this episode, we start connecting two ideas that beginners often keep separate in their heads, which are the technical idea of a model and the practical idea of a business objective. AI systems are built with algorithms and models, but those are not valuable on their own. They only matter if they help an organization achieve a clear goal in a way that is acceptable, safe, and consistent with expectations. Alignment is the word we use to describe whether the model's behavior actually supports the intended goal, rather than accidentally working against it or optimizing for the wrong thing. For brand new learners, it helps to remember that a model is basically a pattern-finding machine that tries to produce an output, but if we do not tell it what success looks like in the right way, it will find a shortcut that looks good in numbers while producing poor real-world outcomes. Task 9 focuses on evaluating alignment, which means learning how to ask the right questions, define the right measurements, and challenge assumptions before trusting a model's results. The goal is not to become an engineer, but to become someone who can reason about whether an AI system is aimed at the right target and whether evidence supports that claim. By the end, you should be able to explain what alignment means, why it matters, and how an evaluator can tell when a model is drifting away from business intent. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A business objective is a statement about what the organization wants to accomplish, and the first step in evaluating alignment is to make that objective specific enough that it can guide decisions. Beginners sometimes think objectives are vague slogans like improve efficiency or reduce risk, but an objective that cannot be tested is not an objective, it is a wish. A more usable objective describes the outcome, the boundaries, and what trade-offs are acceptable, because many AI systems improve one thing by harming another. For example, speeding up decisions might increase error, and reducing fraud might increase false accusations. So alignment means choosing an objective that acknowledges both the desired benefit and the acceptable cost. An evaluator will ask what the organization is truly trying to optimize and what it is trying to avoid, because models do not understand intent the way humans do. If the objective is unclear, the model can still be trained and deployed, but its success will be measured by a proxy that may not reflect real value. This is how misalignment begins, not because the model is evil or broken, but because the goal was never translated into something testable. Once the objective is clearer, the next question is how that objective becomes a target for the algorithm and model. Models are usually trained or tuned using metrics, meaning numbers that act as a stand-in for success, such as accuracy, error rate, or predicted probability. The tricky part is that metrics are not the same as objectives, because metrics are simplified measurements while objectives are messy real-world outcomes. If you choose the wrong metric, the model can become excellent at producing a number that looks good while failing at what people actually care about. For a beginner, a helpful analogy is studying for a test by memorizing trivia, which might boost a practice quiz score but not build understanding, so the score rises while competence does not. Evaluating alignment therefore requires asking whether the chosen metric actually represents the objective in a meaningful way. An evaluator will also ask whether the metric can be gamed by the system's behavior, because models will exploit patterns that maximize the metric even if the behavior is undesirable. Alignment also depends on the context in which the model will be used, because a model's output is rarely the final goal. It is a signal that influences decisions. A model that predicts something accurately might still be misaligned if the way people use its output leads to harmful decisions. For example, a model that predicts likelihood of delay might be accurate, but if the business uses it to deny services automatically, it could create unfair outcomes or reputational harm. Evaluating alignment means understanding the decision process around the model, including who sees the output, how it is interpreted, and what actions it triggers. Auditors and evaluators ask whether the model is being used for the purpose it was designed for, because repurposing is a common source of misalignment. Beginners should understand that alignment is not only a property of the model, it is a property of the system, which includes people, processes, and incentives. If incentives encourage shortcut behavior, the model may be used in a way that is technically successful but practically damaging. When evaluating algorithms and models, it helps to understand that different algorithms bring different trade-offs, and those trade-offs can affect alignment. Some approaches are easier to interpret, some are better at capturing complex patterns, and some are more stable across changing conditions. A beginner does not need to know the math, but should understand that choosing an algorithm is like choosing a tool. The right choice depends on the job and the risk. A simple approach might be aligned if it is transparent and stable, while a more complex approach might be aligned if the objective requires subtle pattern recognition, as long as the organization can monitor and control it. Evaluators ask whether the complexity is justified by the objective and whether the organization has the ability to manage the complexity responsibly. A mismatch can occur when an organization chooses a powerful but fragile model for a high-impact objective without having the governance to supervise it. Alignment, therefore, includes feasibility, meaning the model can be operated safely in the real environment, not just built impressively in a lab. Another major alignment issue is the training data, because models learn from examples, and examples shape behavior. If the training data represents past decisions that were biased, inconsistent, or optimized for a different objective, then the model will learn those patterns and reproduce them. For beginners, it helps to think of training data as the model's experience. If its experience is narrow or distorted, its decisions will be too. Evaluating alignment includes asking whether the data reflects the current objective, current population, and current environment, rather than a historical situation that no longer applies. It also includes asking whether the labels, meaning the outcomes the model learned to predict, truly represent what success looks like. If a business objective is customer satisfaction, but the label is whether a customer called back, the model might learn to reduce callbacks by making it hard to reach support, which would be misaligned. This is a classic example of optimizing a proxy that undermines the real goal. Alignment must also consider constraints, meaning rules about what the model should not do, even if doing it would improve a metric. Constraints can include legal requirements, safety limits, ethical boundaries, and internal policies, and they are part of the objective even if they are not written as a single number. A model aligned to business objectives should respect these constraints because violating them can destroy trust and create long-term harm that outweighs short-term gains. Evaluators therefore look for evidence that constraints were considered during design and testing, such as checks for unfair impact, unsafe recommendations, or misuse of sensitive data. Beginners should recognize that a model that increases profit while violating policy is not aligned, because the objective of a real organization includes staying compliant and maintaining legitimacy. This is why alignment is often described as a balance, where the system must deliver value within boundaries. The evaluator's job is to verify that those boundaries are real and enforced, not just spoken about. A simple but powerful evaluation technique is to compare the model's behavior to the intended objective through scenarios and segments, not as a lab exercise, but as a way to reveal hidden mismatches. If the objective is to reduce risk, you would expect the model to behave conservatively in high-risk cases and to avoid overconfidence when uncertainty is high. If the objective is to improve service speed without sacrificing quality, you would expect the model to reduce delays while maintaining acceptable error rates across different customer groups. Evaluators look for evidence that performance is consistent where it must be consistent, and that trade-offs are acceptable where trade-offs are unavoidable. Segment analysis matters because averages can hide misalignment, such as a model that performs well overall but fails badly for a specific group that the business serves. For beginners, this is like a teacher who grades fairly for most students but consistently misgrades a certain set of assignments, which would be unacceptable even if the overall grade average looks fine. Alignment is proven when the model supports the objective broadly and does not create unacceptable harm in edge cases. Another important part of evaluating alignment is looking for unintended incentives and feedback loops that can push the model away from the objective over time. When a model influences decisions, those decisions can change the data the model later sees, which can create a self-reinforcing cycle. For example, if a model predicts who is risky in the business then monitors those people more heavily, the data will show more problems for that group, reinforcing the model's belief that they are risky. This can be misaligned if the objective includes fairness and accurate risk assessment rather than amplified suspicion. Evaluators ask whether the system design creates these loops and whether controls exist to prevent them from distorting outcomes. Beginners should understand that alignment is not a one-time property, because the system can drift away from the objective as the environment changes and as the model's decisions reshape the environment. Continuous monitoring and periodic reevaluation become part of alignment, because alignment must be maintained, not merely claimed. Misconceptions about alignment often come from treating AI output as truth rather than as a probabilistic guess. A model can be correct often, but that does not mean its decisions are aligned to what the organization actually values. Another misconception is that if a model increases a key metric, then it must be aligned, but that ignores hidden costs like customer trust, employee workload, or compliance risk. Evaluators bring audit-grade skepticism to claims of alignment by asking what was measured, what was ignored, and what assumptions were made. They also ask whether the organization has defined acceptable error, acceptable uncertainty, and acceptable harm, because alignment requires clear thresholds. Beginners can think of this like a medical test that catches many cases but also falsely alarms many healthy people. Whether it is aligned depends on the context, the cost of false alarms, and the ability to handle follow-up. Alignment is about fit-for-purpose behavior, not about perfection. To make this concrete, imagine a model used to recommend which students need extra support in an online learning program. The business objective might be to improve completion rates while keeping the experience positive and fair. If the model labels students as at risk and the program then sends them more reminders, the model might increase completion for some students, but also overwhelm others, leading to frustration and dropout. Evaluating alignment would involve checking whether the reminders help or harm, whether certain groups are targeted unfairly, and whether the model's predictions are being used in a supportive way rather than a punitive way. It would also involve checking whether the training data reflects current student behavior and whether the system is monitored for changes over time. This example shows how alignment is not just a number. It is the relationship between predictions, actions, and outcomes in the real world. An evaluator proves alignment by showing that the system's influence pushes outcomes toward the objective without unacceptable side effects. When you step back, evaluating algorithms and models for alignment to business objectives is about translating intent into evidence and challenging the gap between what we hope the model does and what it actually causes. The evaluator asks whether the objective is clear and testable, whether the metrics represent the objective, whether the data reflects the current reality, and whether constraints like safety and policy are built into the definition of success. They also examine whether the algorithm choice and model complexity fit the organization's ability to govern and monitor the system over time. For beginners, the most important takeaway is that alignment is not a label you attach after the fact. It is a property you must demonstrate with careful reasoning and measurable outcomes. A model that is accurate but misdirected is like a fast car pointed down the wrong road, because speed does not help if direction is wrong. If you can explain how objectives, metrics, data, constraints, and usage context interact, you have the foundation for Task 9, which is ultimately about proving that AI supports the organization's goals responsibly and reliably.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.